Okay, here's another example, a different curve. We need to find dy dx. Okay, that should be fairly straightforward. And then we need to find the range of values of x for which y is increasing. Well, what does that mean? Well, that means that the curve has a gradient which is positive. This is a cubic, so it's going to have a shape which could be like this. And clearly the function changes from an increasing function to a decreasing function and the reverse at the turning points. During this section, we have an increasing function, and also during this section, we have an increasing function. But here, we have a decreasing function. So once we've found the gradient function, we need to find these turning points, because they mark the boundaries that define the regions where the function increases or where the function decreases. So let's find dy dx first. Dy dx is equal to, the 3 comes down and multiplies the 2 to make 6. The 3 is reduced from 3 to 2. So this becomes 6x squared minus 2 times 2, 4. The x comes down by 1 just to make x. So this is 4x minus 2. So to find those turning points, we have to set dy dx equal to 0. Well, the first thing to do is we have a common factor of 2 throughout the entire equation. So we can say that therefore, halve all these coefficients, 3x squared minus 2x minus 1 equals 0. Let's see whether this will factorize easily. This is going to be 1, this is going to be a 1, this is going to be 3x, this is going to be x. So as you know, these two guys produce the negative 2x. This will produce a 3x, this will produce an x, and it will only work if this is negative and this is positive. Just check you get that negative one as well. Yes, you do. So finishing this off, to find the x values of the turning points, if this is true, that these two terms multiplied together equal 0, then either this guy equals 0 or this guy equals 0. If this guy equals 0, x is equal to negative a third. And if this guy equals 0, x is equal to 1. So we know this point is negative a third, and we know that this point is 1. So when is our function increasing? Well, I drew this diagram with a little bit of thought. If you look at the dominant term, which is x cubed, when x is massive, like 1,000, this term dominates the others. And if x is 1,000, this will be massive. So, and indeed, I'm right in assuming it will head up into the heavens. Equally, when x is massively negative, this term also will dominate, and the function will be massively negative. So it goes down there as x goes more and more negative. So I'm reasonably confident from the analysis of the cubic that this region defines an increasing function, as does this region. So my conclusions from my analysis of the cubic is the function increases from the lowest value of x up to, but not including a third, because at this point the function's gradient is 0. Equally, at the point x equals 1, the function's gradient is also 0, but it starts increasing immediately afterwards. So how can I express that mathematically? So the function increases, x is less than equal to negative a third, and x is greater than 1. So there are two regions. It's the outer regions that the function increases. Again, we don't include the goalposts because the function is not increasing at those points because the function's gradient is 0. So that's proof from the cubic. Proof from our differential function goes like this. Our differential function, dy dx, is equal to 6x squared minus 4x minus 2. So our gradient function will be positive during this section, negative during this section, and then positive during this section. It is itself a quadratic, and it goes through the points as we've worked out here, negative a third and positive 1. It's a U-shaped quadratic, so it must look like this. So dy dx is positive here up to this point and only returns positive after this point. And what are those points? Well, they're the roots of the equation we've just worked out. This is x is equal to negative a third, and this is x is equal to 1. What we're really asking is when dy dx is greater than 0. Well, dy dx, which is the blue line here, is greater than 0 up to, but not including the value of x is equal to negative a third, and beyond, again not including x is equal to 1. So the analysis of the gradient function proves the same results as the analysis of what the original graph, the cubic, was up to, having found the turning points of that cubic. So officially they want the answer in set notation, which will look like this: x less than negative a third union with x greater than 1. And that is your answer.